Good luck.
Good afternoon, everyone. I am Shivani, and today I'll be presenting my abstract, Beneath the Red Horizon, Lava Tubes and Regolith as Pathways to Sustainable Martian Habitats. I conducted this project under the mentorship of Dr. Jennifer Blanck at the Blue Marble Space Institute of Science. My project mainly explores what it would mean to build and sustain life beneath the surface on Mars. Each week in the project, we designed and refined a realistic vision for 100% community living either on Moon or Mars. I chose Mars as it's one of the only other planets in our solar system with the right combination of resources, geology, and access to long-term human settlement. We see how uh, people would work, how roles would be distributed across the habitat, and how the entire society will function underground. We also use text to image based AI tools to bring these concepts to life, to iterate and visualize our ideas and test them. We all know that Mars is an extremely hostile planet. Its surface is constantly exposed to radiations, dust storms, and temperatures that can easily destroy unprotected structures. Yet, Mars provides us with ancient lava tubes, which provides us with natural shielding and a very stable environment. So, this brings us to the project in question. Can the geology of Mars itself become architecture? Can the same regolith that we consider dangerous be the very reason of survival and the foundation for a long-term Martian habitat? Now, let me walk you through why the subsurface isn't just an option, but it's a necessity, and how all of these geological features offer a pathway to human life on Mars. The Martian surface challenges almost every engineering idea from Earth. The radiation levels are exceeding the human threshold. Then we have temperatures that can swing from plus 20 degrees Celsius to minus 120 degrees Celsius in the same afternoon. That places a huge amount of stress on the materials and the life support systems. And on top of all of that, we have a lot of micrometeorites that are being bombarded, and we have dust storms that slowly wear down all of the materials and the joints. As the mission duration increases, these weaknesses they don't just stay linear. They begin to amplify dramatically. So if we want to have a long-term stable settlement, we need structures that already offer us natural shielding, stability, and temperature moderation. And fortunately, nature has spent billions of years creating that very structure on the Martian subsurface. This brings us to one of the most promising natural shelters on Mars. It's the ancient lava tubes, our underground shield. Orbital radar and thermal imaging show that Mars has lava tubes that stretch for tens of kilometers and the widths exceed 100 meters. The lava tubes on Mars are much bigger than that of the Earth. There are more than 1,000 lava tubes on Mars. This lava tube is formed from rivers of flowing magma. The outer layers, as they began to cool, they start hardening, while the inner molten, they start leaving behind a cathedral sort of a tunnel. These structures mainly offer us three advantages. The first is natural radiation. These meters of rock overhead, they provide with natural radiation that are much safer than that on the exposed surface. Then we have, secondly, thermal stability. We know that the surface temperature varies from 20 degrees Celsius to minus 120 degrees Celsius. However, the interior portion of the lava tube is stays around minus 20 degrees Celsius year round and doesn't put a lot of stress on the life support systems. Thirdly, the structural integrity. The rocks form under compression, they are incredibly strong and they are much stronger than the lightweight materials that we would transport from the earth. And one of the other advantages they produce is the built-in pressure envelope. In many ways, Mars gives us its own architecture. Our only task is to design how humans will live within it. Now that we understand why lava tubes are such powerful natural shelters, the next question is how we actually build a habitat inside one. The habitat that I design operates on three integrated layers designed to solve a different challenge. The first one is the stabilized ground. The Martian soil is very powdery and loose. However, when we use different construction materials, we can fuse the regolith into solid blocks, and this forms the foundation or the floor for us to build our habitat on. The second layer is the pressurized modular shells. These can be inflatable or they can be very rigid pressure vessels, and they create a livable volume. The temperatures, the air pressure, and life stays stable and it can be easily controlled from within. Lastly, we have regolith-based structural elements. Regolith is used to create different beams, different structures to provide structural integrity without having to export very heavy materials from Earth. Together, these three layers allow us to transform a raw lava tube into a functional Martian habitat. Now, let's look at the raw regolith, the simple dust, and how it can be transformed into a real Martian structure. What really is regolith? Regolith is nothing but the loose, fine soil that covers the entire planet. It's mainly composed of iron oxides, sulfates, silicates, and basaltic minerals. Instead of looking at a regolith as a liability, we can use a regolith as a local construction resource. Uh, there are three different methods that I will be outlining. The first one is through microwave sintering. So in this method, we fuse the regolith grains. We don't use any binders or water. The result is using only energy to produce regolith tiles and building blocks. Next, we have sulfur-based concrete. We mix molten sulfur along with the regolith, and this produces very strong and recyclable blocks as this sulfur cools down to become really hard and strong. The third construction type is the basalt fiber reinforcement. So we melt the regolith and draw fibers from it. We use these fibers along with binders in order to create concrete structures. Beyond these methods, we have metals and metal oxides that are extracted from these regolith and even from nearby asteroids for construction. Once we have created our habitat building and the interior, the next critical element is the pressurized environment where people will actually live. Inside the lava tube, the rock provides the structural shape, but it doesn't really hold the breathable air, the air pressure. That responsibility majorly falls on these pressurized modules. They are shells that act as pressure vessels. So each module is double walled as well as it has a built-in leak before break membrane. This means that even if there's a puncture or there is a small tear, the system stretches slowly and vents instead of immediately rupturing the entire habitat. and doesn't cause an entire habitat catastrophe. So this dual system is what makes the habitat design resilient. Now that we have our habitat structure and the pressure modules, the question that we want to look into is how reliable are these materials that we are building our habitat with? So all of our samples undergo rigorous material testing. These samples form the first generation of in situ Martian materials, and each of these materials are optimized for a specific function and they are tested for that specific function. So each sample is mainly tested based on four critical metrics. The first one is compressive and flexural strength. So can our material carry weight? Can it resist bending large amounts of stress? Secondly, we have permeability and porosity. Does it leak gas? Does it let the dust infiltrate through the spaces in the particles? Then we have thermal cycling. Does it withstand large temperature variations as seen on Mars? Does it crack under these extreme conditions? Lastly, we have outgassing. Does the sample release harmful vapors or gases that can potentially contaminate the habitat, etc. So by validating all of these properties, we turn these samples into predictable and dependable materials for design. Now we have our materials, our pressure systems, and we have tested that it's reliable. So now we are ready to scale up to 100% Martian settlement. In this illustration, we have an architecture of a habitat. It consists of personal pods for the crew members. Then we have separate hygiene modules. Each of the private pods provide a private space for sleeping and psychological well-being. There is a shared gallery, a dining area, and we support routine, culture, and continuity. And we also have engineering bays and scientific labs. These are all isolated so that the work, technical work, doesn't really interfere with our daily life. This helps us build community health and improve creativity and a good habitat environment. So this forms the layout of the habitat. Now I will talk about our environmental life support system, or ELSS, as I like to call it. So this is a closed loop network that continuously recycles air, water, and waste in order to make the habitat self-sustaining. So first we have the water recovery unit. So this unit, it brings water from cleaning, washing, and from hygiene condensates, and it begins to distill and filter this water until it becomes drinking grade quality. And parallel to this, we have the air revitalization unit that consists of a molecular sieve that traps the carbon dioxide, and through electrolysis, it generates oxygen. So in order to maintain a stable atmosphere. Now we have the organic waste unit. It collects the food scraps, plant matter, our biological byproducts. All of this is made into a nutrient-rich slurry, which is fed into the hydroponics, the agricultural systems. So this produces fresh oxygen, edible greens, and a closed, sustainable habitat. Now, even with a perfect life support system, a settlement cannot survive on engineering alone. Thus, we study different analog missions. Studying analog missions like high seas, ESA caves missions, and habitat marquee, we one lesson continues to appear again and again. That is, the long duration endurance of the crew members depends not only on technology and engineering, but also psychology. So we have integrated behavioral changes directly into our architectural structure. So first we have a programmable circadian lighting that simulates Earth-like day and night rhythm. This stabilizes our sleep, our hormones, and improves our mood. Second, we have sleeping pods and isolated crew a crew private retreat that gives the crew members rest, recovery time, and just a quiet place for themselves. Then we also have communal kitchens, lounges, recreational spaces, and a lot of greenery to provide comfort and an earth-like feeling. The settlement is fully organized around routine, a shared sense of space, and also different lifestyle elements, and not only engineering tools. And this increases the reliability of the habitat as well as helps us not only live in the habitat but also to thrive. Now, I'm going to come to the conclusion of my presentation. We have seen that Mars is really harsh and it's really unpredictable and its surface is unforgiving. But by using lava tubes as a subsurface habitat and regolith as our foundation, we begin to see Mars not as a hostile world, but a world that we can adapt to. So, to this project, we see that sustainable Martian living doesn't come from fighting this planet, it comes from working with it. It uses its geology, respects its constraints, and shaping its natural architecture into a place where we can live, grow, and thrive. Beneath the red horizon, Mars already holds the shelter. All we need to bring is the humanity. I would like to thank everyone for this opportunity to present my abstract. I would also like to thank my mentor, Dr. Jennifer Blanck, and Blue Marble Space Institute for all of their help and support. Thank you.